And hopefully you also hear audio. Let me know. Fantastic. Okay, that's really great. Okay, you want to look at questions 2 and 9 on homework 11. Okay. Uh, Great. So let me go to homework 11. Here's homework 11. And okay. And let's see. You want to look at problem 2. Okay. Uh, Compute the following limit. If it does not exist, write dne. All right. So for this problem, it's a shame there's no hints here, isn't it? For this problem, the limit does exist, and one way to see this is that you can factor the numerator. You can write this numerator. I don't know if you can tell this, but the numerator has a factor of x plus 2y. It's actually x plus 2y squared. So it's cancels this denominator, which is 2x plus 4y. So the denominator factors is, say, 2 times x plus 2y. And then when you're able to cancel one of these factors, then you can calculate the limit because those two functions agree for all nearby points. Let me maybe draw a little picture of this just to give you an idea of how this works. I mean, it's an extremely common kind of format and method anyway that ends up being used to address problems like this. Yeah, so you're saying if it doesn't cancel, it probably doesn't exist. I mean, that's a fine heuristic. The challenge is that it can be pretty hard to determine how these things factor. So when this problem is asking you to take a look at the limit as xy approaches 0, 0 of what was it, x squared plus 4xy plus 4y squared all over 2x plus 4y. And the thing to think about here is that I can do some factorization. So this is the same as the limit of same thing here, xy goes to 0, 0. And I'll factor this numerator. This numerator factors as x plus 2y squared. And the denominator I could write as x times x plus 2y. Now here's the really exciting step. I'm going to write this as the limit of the same thing of x plus 2y divided by 2. So, I mean, so to speak, I'm canceling these things, right? But what's important here to think about is why these equalities are holding. So this first equality holds because this is exactly the same thing as this. This equality, however, holds not because this is the same thing as this, but because this thing is equal to this thing whenever xy is close to but not equal to 0, 0. And when you're calculating limits, the only thing that matters are values that are close to 0, 0, right? The limit is entirely insensitive to the value of this thing at the point 0, 0. Or said differently, this thing here isn't defined at 0, 0, right? If I plug in 0 for x and for y, this thing is 0 over 0, which is a meaningless quantity. This thing is equal to 0. And the limit is only sensitive to values that are around 0, 0, right? It doesn't matter what this thing is actually at the point 0, 0. And the fact that this thing agrees with this thing as long as x, y, well, strictly speaking, as long as x plus 2y isn't 0, that is good enough for our purposes. Okay. Let me let me go back here and try to take a look at some of these other problems now. Oh, we got some more questions. You are wanting to do some differentiation and some kind of L'Hopital. You know, I'm not sure I've really said as many horrible things about L'Hopital as I really feel in this course so far. But if you go to the internet and maybe I can find some video which will include, oh, here, this video, yeah. So this is a video where I'm going to complain about L'Hopital's rule for a while. Anyway, the point is that L'Hopital's rule is really horrible. So don't, I don't really want you using L'Hopital's rule generally in your lives, unless you're careful to think about why you're using it. I mean, for these kinds of problems, one technique certainly is being able to do some kind of algebraic manipulation. We don't have actually that many techniques for evaluating limits. I mean, most of our techniques involve the limit laws, and then this one other limit law that says I can substitute something like this for this as long as they're equal for nearby values. I mean, and I also I should also be warning you, that in a situation like this, that denominator 2x plus 4y. I mean that denominator is 0. Anytime say 2x is equal to negative 4y, and the fact that there's a whole line where this thing is undefined, maybe should bother you a little bit too. But okay, let's see. What else? So if the limit exists at 0, 0, then it's not continuous there. So for this function, for example, for this thing here to be continuous, it would have to be the case that this thing is defined at the point 0, 0. So you could, fix this up a bit. You could, for example, build a slightly fancier function. I could build a function like, I guess I'll call it g, and g will be, this other thing, x squared plus 4xy plus y squared over 2x plus 2y, as long as xy is not 0, 0, and it'll be 0 at the point 0, 0. And then this thing, I'm okay saying that this thing is continuous at the point 0. Okay, let's see what other questions did we have here. Question 9 also on homework 11. Let's go back to that. I don't know where there it is. Okay. Let's go back to homework 9 on homework 11. Consider this function, compute this limit. Okay. So this is it's actually a very similar kind of setup. So here, this thing, xy squared minus y to the fourth divided by x squared minus y to the fourth, that also factors. Let's see how. So this thing is x y squared minus y to the fourth divided by x squared minus y to the fourth. Okay, and I can factor that, and when I factor that, I guess I'll write y squared on the top times x minus y squared. And in the denominator, this is a difference of squares, so I could write that as x plus y squared, x minus y squared. And what that means is that the limit as xy approaches 4, 2 of this thing, xy squared minus y to the fourth over x squared minus y to the fourth, that's the same as the limit, well, of this, but I can factor these. Now, this is pretty terrifying because I've written an equality here and I've crossed these things out. And this is not, strictly speaking, the same as this, because this thing is defined at places that this thing isn't. But in terms of the limits, they're going to be equal because this thing agrees with this thing for values of x, y that are close to 4, 2. So these limits will agree. And in this thing here, actually, there's no problem computing the limit of this because this is a limit of a quotient where the limit of the denominator exists and isn't 0. So this is the same as the limit of y squared as y approaches 2 divided by the limit of x plus y squared. And this denominator is the limit of a sum, which is the sum of the limits provided the limits exist. This is the limit of x, this is the limit of y squared. So this whole thing ends up being 2 squared divided by 4 plus 2 squared. Okay. Yeah, the factorization of these things, I mean, can be quite tricky. So I mean, I think you're right to point out, whoa, I mean, how do we factor that thing? I mean, it's it certainly involves some insight, and instead of insight, you can practice and recognizing this is a difference of squares. So it's the same as a squared minus b squared is a plus b times a minus b. It's kind of a classic trick. Yeah, and then again, this thing's not continuous because although the limit exists as xy approaches 4, 2, this quantity isn't defined at the point 4, 2 because I mean, for this is 0 divided by 0, which is a meaningless quantity. I don't know how many zeros go into 0. Okay. Well, it's worse than a surface with a little hole because it's actually undefined along this entire parabola where x equals y squared. And it is, I mean, honestly, it's a little bit upsetting to try to think about these things too much because it's, in this case, the thing is the domain of this function, is pretty painful, right? I have to worry about when the denominator vanishes, and here the denominator is vanishing along a couple parabolas. Okay. Let's see. Homework 7, problem 5 is another request. Let's look at that. Homework 7. Go back to my assignments tab here on Carmen. Homework 7. Problem 5. Yeah, this is the one, hopefully, that you want to look at. And you want to find the length of the curve drawn by f as t runs from 0 to 1. This is kind of a funny problem because this thing here actually traces out just a line segment, which goes when t is equal to 0 from the point 0, 0, 0, when t is equal to 1 to the point 1, 1, 1. So I'm really, oh, it's the third problem. You want this I'm getting so excited about doing that problem. You want to think about this problem. That's okay. I was happy about that one. Oh, I better click this update button. Somebody changed this problem. Okay, the starting position of a particle is given by this. Okay, so starting at the origin, and its acceleration is determined by this function. And then I'm going to suppose that the initial velocity is this. Now I'm going to write down the velocity function. So my initial guess would be something like this, but then I want to, whoops, nope, I'm trying to integrate this. So I'll write minus 3t 0 minus 3t squared. But then I've also got to make sure that I get these initial conditions correct when time equals 0. So I'll add some of these initial conditions to it. All right. Now the speed is going to be the length of my velocity vector, which I will just typing in my velocity vector, and I hope, okay, I did that. Now I'm going to integrate velocity to get position up to some constant. So I'll write minus t squared over 2 plus 60t, and then I'm told that the position at time 0 is 0, so that looks good. Here the velocity is 10, so 10t, and then here I guess I'll write minus t cubed plus 75t in order to get the position. And then it's asking me about the maximum z height. So that's really asking me how large can minus t cubed plus 75t be when t is bigger than or equal to 0. And well, I can show you a plot of this on Desmos if you like, and it's a cubic, so you're not going to be too surprised. Let's see, it's 75t minus t cubed, and whoops, I better make that an x so that it it actually plots it. So what I want to show you is just, I mean, you probably know what a cubic looks like, but it wow, that's pretty funny. Look at how tall it gets. Right, so it looks like it gets all the way up to 250 before going down. Now, how would I ever figure out how tall that thing is? Well, I could use the power of calculus, to figure it out, or I guess I could look at this graph. But when I differentiate this, which is really exactly what I've got here, I could ask, when is its upward velocity equal to 0? And that's when t equals 5, right? Because then minus 3 times 5 squared plus 75 is equal to 0. So its maximum height must be when t is equal to 5, and that'll be 75 times 5 minus 125, which is 5 cubed. Hopefully that helps with this problem. We're going to look at problem 5 on this homework. Let C be a curve drawn by this. Oh, find the length. This is great. This is the one I was excited to do. So why that happened is because this curve is actually just a line segment. I bet you can even do this in Desmos. Let's see. I mean, if I do maybe a special case. Oh, maybe not. I don't know how I plot parametric functions in Desmos. See, I don't really use this Desmos thing. Maybe I can't plot parametric functions. Maybe I can. Does this plot a parametric function? No, not too much. Well, anyway. Oh, well. I'll leave that. So, but this thing does, in fact, it is just a line segment. I was hoping to show an example of that just in the plane. So this looks just a complicated way of parameterizing a line segment. So when it goes from 0 to 1, it goes from 0, 0, 0 to 1, 1, 1, and the length of the line segment from 0, 0, 0 to 1, 1, 1 is the square root of 1 squared plus 1 squared plus 1 squared, square root of 3. Now, is f parameterized by arc length? I mean, it could have been parameterized by arc length, but this is definitely not an arc length parameterization. I can tell that because it's not constant speed. if I differentiate this, I get 2t, 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 and that thing has a very different speed when t is equal to 0 compared to when, say, t is equal to 1. It starts off slow and then it speeds up. So this is, no, it's not parameterized by arc length. Ooh, now it wants to give me, it wants a new description of C, so that S is an arc length parameter when S is, say, between 0 and, why is there a less than or equal to symbol there? That's a weird choice, isn't it? Oh, I see. It's really just talking about this curve, so it wants this thing to be between that and the square root of 3. Okay, that's fine. And let's see, so I'm going to give a new description of C so that S is an arc length parameter. And I mean, it's a line segment, so all I've got to make sure is that I move along the line segment at unit speed, say, so I can do this. And this will move me along the line segment at unit speed. This thing here is still moving along the line segment. You might have guessed that the answer might have been SSS, but I've got to modify it slightly so that it's moving at unit speed, so that it's an arc length parameter. I don't know if that helps. Maybe if I draw a picture, then you'll feel better about this. So if I draw a picture of this, here's space, right? Here's the origin. Here's the point 1, 1, 1. Here's the line that I'm moving along. Right? Here's, what I'd like is to figure out what point is S away from the origin along this line. Well, I know the coordinates on this line have, they've all got the form, if you like. I got to pick a name for a point that isn't X, Y, or Z. Okay, I'm going to call it W. Okay, so every point on this line segment has the form WWW. It's like the internet. And what I want to make sure is that I want to figure out where W is so that this thing here has length S. That's what an arc length parameter is, right? It figures out the point on the curve that's exactly S units along the curve. And, well, if I think about, how far away is the point WWW from the origin, well, it's the square root of 3W squared. W's positive. It's W times the square root of 3, and I want that to be equal to S. And then I could just, divide by the square root of 3 on both sides. Then I find that W is equal to S over the square root of 3. So that tells me that what I really want here isn't WWW. I mean, what I really want is S over the square root of 3, S over the square root of 3, S over the square root of 3. And that point is on this line segment, and it's S units away from the origin, which is exactly what I want in an arc length parameterization. Okay, hopefully that helps a bit. Let's see. Oh, more. Homework 11 due tomorrow. Question 8, which asks what level. Oh, those are fun. Let's look at that. Assignments. Homework 11. It's going to load homework 11. Problem 8. Consider F. Let C be the curve defined by that. Oh, great. Yeah, so I check to see if it's a level curve. And I can check to see that it's a level curve just because I can take, points on this curve have the form 2tt, and then I plug them into this equation, and I verify that it always gives me the same output value. Yeah, that means that it's a level curve. Now it's asking which level curve is it, and what it's really asking me there is that when you're sitting on this curve, the image of P of t, what are the outputs of F? And what I do is I'm going to take a point on this curve, which is 2tt, and I'm going to plug it in here. And what I find is that I get 2t cubed t minus t cubed 2t divided by t to the fourth plus 2t to the fourth. And all those t's end up canceling. So every output, I mean, as long as t is bigger than 0, every output is this. It turns out to be 8 minus 2 divided by 17. So that's what they mean by which level curve of it is it. It's the level curve that corresponds to the outputs of this function, which are 8 minus 2 divided by 17, because this is exactly what this function outputs when you're moving along this curve, as long as t is bigger than 0. And then it's asking you to compute the limit. And, well, you can compute this limit, say, by moving along this curve, if you like, but then you might be terrified to see what happens when you move along some other curve. And depending as to which curve you're approaching the origin along, you're going to get different values of your function. And that's real bad news if the limit exists, right? If this limit existed, if it equaled some number L, well, what that would mean is that you can make f of xy as close as you like to L, as long as xy is close enough to 0, 0. But because you get different values very different values of f, depending as to which level curve you're walking along, right? If you walk along some other path towards the origin, you get totally different values here. That's going to be real bad, because it means that you can't guarantee that when xy is close to 0, 0, you really can't tell me much of anything about what f is close to. And then it's asking here, is this function continuous? And I mean, this function's at least defined on r squared, which is, I guess, an advantage compared to f, which was defined on the punctured plane that didn't include the origin. So this is, I guess, this is defined everywhere, but it's definitely not continuous, because the limit doesn't exist. And one of the condition for being continuous is that the limit exists and it equals the function's value at this point. I mean, f doesn't even have a defined value at the origin. This rule only defines a function, which it makes sense when xy is not 0, 0. G, I can plug in 0, 0, and I get 0 out, but the limit still doesn't exist. It's going to be bad. Let's see. So yeah, you're finding it hard to think about the image of this function in 3D. Yeah, I agree. I think it's pretty hard to visualize that function. I mean, we could try using some software if you want to try and think about what this looks like. Let's see. I think I use this in GNU Plot. I just never really know. Oh yeah, that worked. Okay. So yeah, that's unfortunate. Let me try it again here. Ooh, well, that's really crazy looking, isn't it? Let's try it one more time. If I move these things away, I mean, that looks pretty good. I keep messing up where I am. Oh, I'm so lost. Oh, there we go. Yeah, I don't know. This is not the best. Not the best plot I've ever seen. Let's try Sage. Maybe Sage will do a better job of plotting this thing, so you can get a picture of what it looks like. Let's see. Plot 3D, I guess. Let's see. Oh. Oh. Let's see how to plot. I don't really remember. Oh, that makes sense. Okay. Let's try this. See if we get a reasonable looking picture. Oh, that completely failed. That's depressing. Graphics 3D object. I was hoping would actually display some kind of object. Oh well. Okay. Let's see. Yeah, I mean, oh, okay. So you want to know how you'd maybe think about what that level curve is? I mean, you have to solve some algebraic equations, and I mean, I don't have any great advice along those lines. Um, I mean, except that it's hopefully possible. Let's see. Uh, oh, yeah, okay. Problem number three. Uh, have asked you to find a limit along a line. That's definitely an important idea. So let's do some examples like that. Problem three. Okay. So yeah, it wants you to try to compute this limit. So this limit doesn't exist, and the reason is because this expression's value. Uh, what happens to it when you start to approach 0, 0 is pretty terrifying depending on which line you're approaching 0, 0 along. So let me draw a picture here again, and move this over there. Uh-oh. Okay, so what's happening here is if I draw maybe just coordinate axes, and then I can pick, say, this, and think of this as the line y equals x, and then I could think about this and think of this as y equals 2x. So here, this is my y-axis, this is supposed to be my x-axis, and I've got two different lines. So this is, if you like, when m equals 1, and this line is the line when m equals 2. So that's y equals 2x. And the issue is that this quantity has very different behavior when you're marching towards 0, 0 along this line as compared to when you're marching along 0, 0 along that line. And we can see that by plugging in, say, y equals x into this expression to try to explore what happens when I move towards 0, 0 along this line. And I'm walking as if I'm going from say the right hand side, but of course when I'm computing the limits, I'm really just computing the limit along this entire line at that point. So if you like, I could even parameterize the line. I could write p of t equals t t. So that's a parameterization of this line when y equals x. And then I could ask about the limit as t approaches 0. Let's call this quantity big F of big F of p of t. And that would be the limit of 2t squared plus 3t squared divided by 4t squared minus 3t squared. So here all of my x's and y's just become t's, since I'm moving along this line where x equals y. And I'm asking what happens when t approaches 0. And what's really important is that this limit, the limit as t approaches 0 of this quantity, is an entirely different beast from this limit, the limit as xy approaches 0, 0. To assert that this limit equals something, if I were to say this equaled something, if I were to say it actually existed, that would be a promise that no matter how you approach, no matter how xy approaches 0, 0, you can make this expression as close to whatever it equals, as long as you make xy close enough to 0, 0. This statement here about the limit as t approaches 0 of f of p of t is only making a promise about what happens along this line. It's not saying anything about what happens when I come towards 0, 0 along some other crazy path. And that's extremely important, right? This thing here is a much stronger statement, and to say it exists is to say a lot more than to say that this limit exists, which is only saying something about what happens along this line. Now, this limit, although it maybe looks kind of terrible, I can actually compute this limit because there's a common factor of t squared everywhere, I can factor out all those t squareds and then use the usual business that a limit is only sensitive to nearby values, right? When I compute the limit, I can swap out this expression for anything which is equal to this expression away from the point t equals 0. So I can factor out all the t squareds and then cancel them and then evaluate the limit that way. And I find that I get 2 plus 3 divided by 4 minus 3. And 2 plus 3 is 5, and 4 minus 3 is 1. So this is exactly where this statement is coming from. When m equals 1, the limit is 5. And in fact, I mean, when I'm on this line, the function's value along this entire line is 5. This expression is constant when t isn't equal to 0, right? And I mean, this is actually just a level curve, for this function, right? The function's value along this whole line is 5. Now something horribly different happens along this line where y equals 2x. And then if you wanted, I could parameterize this curve here. Maybe I could parameterize it by q. Q of t equals, and then I could use t again for x, and then 2t for y. And that'll parameterize this line. It also passes through 0, 0. But the function's behavior along this line is very different from the function's behavior along this line. So then I would again be calculating a limit as t approaches 0, but to explore the function's behavior along this line, I would be computing the limit of big F of q of t. And when I do that, I'm plugging in t for x, but 2t for y into this expression. And that's where this thing comes from. It comes from plugging in t for x and 2t for y, and then seeing what happens when t approaches 0. And I discovered that along this line, I get a different value for the function along this line. Maybe here's another picture that maybe would be nicer. I mean, maybe this is going to be a great picture. I'm going to try to draw a three-dimensional picture, right? So I mean, what's happening here is that along, here's, maybe I'll draw it down here. Here's supposed to be the line y equals x, and then I've got the function above here, and then here I've got this other line, which I'll think of as y equals 2x, right? And then the function's value there is something else. Now, at the point 0, 0, the function's not defined. But what's really crazy, is that if you walk towards 0, 0 along this ridge, you're walking at a different elevation than if you walk towards 0, 0 here. Right? And the function isn't defined at the point 0, 0. But then depending as to which line segment you're walking along, you get completely different values of this function. And it's constant on these line segments, which is, itself maybe kind of surprising. But then around the point 0, 0, exactly what you're close to depends on which of these lines you're sitting on. And in that sense, it doesn't really make sense to say that the limit exists of this expression as xy approaches 0, 0, because if you tell me that this expression, is close to 17 when xy is close to 0, 0, well, I'll just tell you, well, what if we're near 0, 0, but on this other line? Then you're very far from 17. And a limit is a promise, right? It's a promise that you can make this expression as close as you like to whatever you tell me the limit is equal to. But you can't tell me this thing's close to anything when xy is close to 0, 0. And it really just depends on what line you're moving along. More things happened here. Yeah, there's just a lot. I'm not sure. I wish I had some nicer graphing software on this computer. I'd show you some more pictures of these things. But it's actually good to draw the pictures by hand, to get a sense of what's going on. Let's see. When it asks you to find the limit along the line y equals mx, yeah, that's what this means. Yeah, you're going to plug in mx for y. Oh, yeah, I see. And then Sarah's telling us exactly what to do here. So yeah, then you're supposed to simplify it, figure out what happens to all those m's, and then hopefully, maybe you'll find the limit's different. And if the limit's different, that's good, because then then you get some kind of wonderful conclusion, like the limit doesn't exist. Okay, great. Other questions that folks have? Oh, the last problem. Oh, okay. I'm guessing on this homework set is what you're wondering about. You wanna compute this limit. I think the easiest way to think about this is to note that this denominator x squared minus y to the fourth factors. All right. So if I pull up another sheet of paper here, right, x y squared minus y to the fourth. Well, that's the same thing as y squared. This you probably won't be as excited about, times x minus y squared. And then more dramatically, the denominator, x squared minus y to the fourth, well, that factors as a difference of squares. It's x minus y squared times x plus y squared. I've written that so terribly. Let me try that again. So it's equal to x plus y squared times x minus y squared. And that means when you're trying to explore this limit here, well, then you can use the fact that this factor and this factor are the same. So you can do something like this. So you want to explore the limit as xy approaches 4, 2 of f of xy. I've written this really badly. That's the same thing. Oh, and now, okay, now maybe you're less excited. 4, 2 here, and then the numerator after canceling becomes, I guess, just y squared, and the denominator becomes x plus y squared. And now this thing here it's actually continuous at the point 4, 2, so you can evaluate this limit, as you like to say, just by plugging in. And of course, the equality of this and this isn't because this is equal to this. It's just that this thing and this thing agree for values near 4, 2. This thing's actually defined at a lot more values near 4, 2 than this thing is. But at least anywhere where this thing is defined, this thing is also defined, but this thing's defined at even more places. And in particular, this thing is defined at the point 4, 2. So you can use this function to compute the limit of this around the point 4, 2. Okay. Hopefully you're feeling better about those kinds of limit arguments. This idea that you're swapping out a function for a function which is, related, so the values line up, except something good happens at that point. It's a common trope in these kinds of limit calculations, and it's practically the only tool we have. The only other tool would be the squeeze theorem, but we're not really doing too much with the squeeze theorem for these. Yeah, this thing's sorry, I didn't talk about the second part of this problem here. This thing's not continuous because this thing isn't even defined at the point 4, 2. I can't plug in 4, 2 here because the denominator vanishes and I'm not allowed to divide by 0. So the function big F isn't defined at the point 4, 2. It's something that we don't probably emphasize enough, in these kinds of courses, right? Even in single variable calculus, I could do something silly like build a function f of x equals x over x. Now, strictly speaking, this isn't a function. This is a rule for defining a function, but I could think of f as a function from the reals minus 0 to the real numbers. I'm not allowed to plug in 0, so I subtracted off the point 0 from the domain of this function because this thing here isn't defined when x is equal to 0. And the reason that I'm saying this is because people have a very strong temptation to say that x divided by x is equal to 1. And this is true, right, as long as long as x, isn't 0. If x is 0, this is just nonsense over here. Another way to say it is that people might be tempted to write f of x is equal to 1. Or maybe people might write another function, g of x, which is the function that's just 1. And then maybe they would be tempted to say that f is equal to g. And it is true that f and g agree for lots and lots of values of x, but the domain of g is different. G, by this rule, could be defined for all real numbers. So depending as to what you tell me the domain of g is, f and g may actually be different functions. The domain is part of the data that determines when functions are equal. Functions are only equal if they have the same domain, and for each point in the domain, they give the same output. Oh, the student's work in problem 7. I thought this was a hilarious problem. So yeah, let's take a look at this fake student's work. I think we all, well, anyway. Okay. So yeah. So the problem here is that this student has only looked along two paths. They explored this function given by the rule that sends xy to 6xy divided by 5x squared plus 4y squared only by searching what happens along the line x equals 0 and along the line y equals 0. But there really isn't such a thing as a two-path test that would tell you that a limit exists. There's only really a two-path test that can fail when you get two different limits along two different paths, and in that case, the limit would not exist. But just checking two paths isn't enough to conclude that this limit exists. And in fact, in the second part of this problem, you're asked to explore this same function but along other paths that aren't just the path x equals 0 or along the line y equals 0. And when you explore the situation along other paths, you discover to your horror that this function's value depends in a very sensitive way as to exactly which line you're moving towards the origin along, and consequently the limit doesn't exist. Another way to say this is that this student could have succeeded to use the two-path test to show that this limit doesn't exist if they had just chosen some other path, say the path x equaled y, and when you move along the origin along x equals y, then you're looking at the limit of 6t squared divided by 5t squared plus 4t squared, which is definitely not 0. Hopefully that helps. Okay, no problem. Yeah, I know I like these kinds of things a lot. I mean, there's a lot of neat things to think about. How complicated can your limits be in these kinds of problems? Can you cook up a function so that for example, you could just draw some kind of crazy curve, and can you cook up a function so that along this sort of crazy curve like this, the function's value is say equal to 0, but when you come along some other curve, you get some other value for your function. So you can, that's kind of sort of a fun thing, right? I mean, how complicated can you make these sorts of functions? And this is a nice example because it's an example that shows you that just checking the axes definitely isn't enough. And then with more work, you could cook up some examples where just checking along lines won't even be enough. You might have to check more complicated paths than just lines to the origin. Those are fun too. Other questions that people have? Online homework. Do you mean in Chimera here what? Hold on. You mean what this online textbook thing is? Okay. Yeah. So, I mean, if I click on this, then I get sent to the textbook. Well, I better click this update button. That's great. Oh, continuity. There's a section on continuity now. And we better click this update button. Okay. Oh, you're wondering about curves in the plane. Okay, I can go back there. Whoa. Which one are you wondering about? Oh, lines and curves in space? This one? Okay, yeah, no problem. These are pretty fun. I'm excited about doing partial derivatives tomorrow. That's going to be really great. There's a lot of really great stories with partial derivatives. I mean, continuity is really, really great too. And all this limit stuff is a lot of fun. It's too bad really that we can't say more precise things about exactly what limits are in this case. I mean, because we only I think in here there's only a few. I mean, this is a good thing to think about, right? The fact that the domains can be quite complicated, and what open sets are, I think, is really fun. But when you see, I mean, we've got these laws here for calculating limits, and then the main one, that we're really using in a lot of applications is one where we're swapping out one quantity for another quantity as long as the two functions agree near but not at that point. Oh, okay, plane in space. Let me go back up here. Planes in space. Okay. Okay. What are you wondering about on planes in space? Oh yeah, we can look at the parametric plots. Let's see these things down here. Is this what you're wondering about? That's two graphs. See, I think I have to click on these things to make the graphs appear. Yeah. Wonder where do the graphs appear? Do they appear here? Oh no. Now I have to calculate. Oh, these are so awful. I have to actually do division. Let's see. Yeah, this one I guess could be. What about this one? It's so hard to divide in my head. That one looks okay. Let's see this one. I mean, they all look okay. Which one of these is no good? Let's see. This one is the the bottom. No, this one looks to be okay. Let's see, -6. Are these ratios the same as these? That looks okay. That seems okay. Hmm. Okay, oh, you're wondering about, let's see, down here to modify. Oh, do you mean when I click on this and see the graph? Is this what you're wondering about? These kinds of graphs? Last two questions. Yeah, where you modify the code, you mean to see them? I'm not sure where the LST formula appears in this. Last two questions. Yeah? Okay. Uh, so I want to give an implicit equation for the plane that passes through the point 1, 2, 3 and is normal to this. So let's see. So I want to draw an arrow from 1, 2, 3. So I'm going to take 1 plus 0, 2 plus minus 2, 3 plus minus 4. That's going to draw for me a vector which starts at the point, so that blue thing there is now a vector that starts at the point 1, 2, 3 and then ends at 1, 2, 3 plus 0, minus 2, minus 4, which is what this normal vector is. And then I want to make sure this thing's actually normal and passes through the point 1, 2, 3. So I'm going to write x minus 1, y minus 2, z minus 3 to make sure that it passes through that point when it's equal to 0. And then I want to dot this with this normal vector. So 0, minus 2, minus 4 will successfully write down the dot product of 0, minus 2, minus 4 with xyz minus 1, 2, 3. And then, oh, look at that. That's so great. So now my plane is in fact normal, and you can tell it there, but it's normal to that blue vector is really perpendicular, right, to that plane. So I've successfully written down an equation that defines a plane implicitly. So the equation is this: f is equal to 0, and the vector, which I wrote down, is the normal vector. Is that the sort of thing you're wondering about? Okay, great. Now let's look at this next one. Ooh, now I'm going to give it a parametric. Oh, I see. This is the LST thing you're saying. Great, great. Okay. So let's see. Now is 1, 0, minus 1. Okay, so this vector is now pointing in the correct direction. It's 1, 2, 3, and then this is 1, 2, 3 plus 0, minus 2, minus what is the other one here? Minus 4. Okay, so that looks good. So that's the right. And then here I've got a point that I want to go through, 1, 2, 3. Oh, and then I've got these two directions. So one of them is, well, I mean, one way to write this, if you don't like writing it like this, I mean, I could write it as 1, 1, 1 times t, and I could write it as 1, 1 times s. And then I'm building the plane now by taking a point and adding something times t plus something times s. And I just need to make sure that these things are that 1, 1, 1, so to speak, and 0, 1, 1 are vectors that point in the direction of the plane. Now hopefully, oh, here they are. Here are the vectors that I want to be moving in the directions of, right? I've got v and w, and I built v cross w to be perpendicular to v and to w. So if I build my plane so that one of the directions in the direction of my plane is 1, minus 2, 1, and another direction which is pointing along my plane is minus 1, minus 2, 1, I'll be good. So let's use 1, minus 2, 1. So I'll write 1, minus 2, 1 for one of them, and then the other one I'll use minus 1, minus 2, 1. So minus 2, minus 1, 1. And, whoops, sorry, minus 1, minus 2, 1. Okay, minus 1, minus 2, 1. That's, okay, so that's the v and w up there. And then when I evaluate this, I'll get, oh, look at that. That looks great. Oh, why can't I wiggle it around though? I'm gonna. That's a shame. Uh-oh. Okay. Try evaluating that again. Hopefully now it will rotate. Nope. Now my computer is really unhappy. In any case, it looks pretty good and perpendicular there, which is what I wanted. Hopefully that helps you think about this. So this is really, say, the vector v, this is the vector w, but I multiply them by t and s so that I end up starting at that point and then moving some amount in the direction v and some amount in the direction w by using t and s as the parameters for how much I want to move in the direction v and the direction w, respectively. Let's see, there's also a question to look at parametric plots, and then the last question at the bottom. Hopefully that helps with the curves in space business. Let's look at parametric plots. Oh yeah, this is another one of these things. Is it? Let's see, which problem is it? That is this problem here that you want to look at, Max? So here. No problem. Let's see what's going to happen when this thing is done. Oh, that's great. Look at that. It made a tube around the parabola. Isn't that fantastic? Oh, I can make the tube. I can change how big the tube is. So this 0.5, let's make a bigger tube. I make it 0.8 now. Now it's going to be a bigger tube. Oh, that's great. Look at how it's got that kink there. That's really funny, isn't it? That's, oh, yeah. That seems bad, doesn't it? Let's make the tube even bigger. Let's make it 1.8. Oh, look at how horrible that is. That's terrible. Okay, got a big kink in it now. Yeah, so how we built that, it's actually it is related certainly to the previous problem because I started with a point. Now, instead of starting with one point, I'm starting with a point f of t, which is on the curve that I parameterized in space. So it's coming along the curve that's the image of t squared minus 2, t squared minus 2, and minus t. And so that's f of t, and then I'm adding to it, something in the normal direction, so n times 1.8 times cosine s, and then something in the binormal direction, bn times 1.8 sine of s. And maybe I draw a picture here just to give you a sense of how this is working. Whoops. So I've got this curve. So in this case, this is f of t is the image of f of t is this curve. So then I've got some point f of t on this curve, and I've certainly got a tangent direction. So that's the derivative, say normalized to be unit length, And then I've also got a normal direction and a binormal direction. So maybe this is N and this is B. And then to build the tube around this thing, what I'm doing is I'm using N as if it were, say, the x coordinate, the x direction. And I'm using B as if it were the y direction, and then I'm combining them, in the same sort of way that I would normally be building a circle. So up here, I've got, whoops. So up here, I've got my function f of t, so that gives me this point here. And then I'm adding to it some amount in the normal direction and some amount in the binormal direction. And then I'm scaling those using cosines and sines, so that by choosing different values of s, I'm effectively moving myself to some point. So if this angle here is s, I'm moving myself around a circle which sits in the plane spanned by n and b. And then by changing s, I end up moving around this circle. And then by changing t, I end up moving around this curve in space. So by picking different values of t, I move along this curve, and then picking different values of x, I move around these circles. But I'm building these circles by combining the normal vector and the binormal vector in space, in the same way that I would combine something in the x direction and something in the y direction to make a circle. So I'm multiplying the normal direction by cosine and the binormal direction by sine in order to move around a circle in the plane spanned by n and b. And that ends up working really great. It ends up building for me this tube around my curve in space, and then by picking a different curve in space. So here I'm using the curve t squared minus 2, t squared minus 2, 1 minus t. Let's make a thinner tube again. But I could make this be some other curve in space. Here's some other. Oh no. Oh, whoops. Put an extra h in there somehow. So here I'm using cosine t, sine 5t. And oh, that looks horrible. Well, it looks horrible, I guess, partly because I've got this tube to be way too thick now. Let me make my tube much thinner. So I'm multiplying the normal and binormal directions by 0.05 cosine and 0.05 sine. That'll make them thinner. Hopefully this looks better. It looks a little bit better. It's not my greatest artwork ever. But you can see that I built a tube around cosine t, sine t, and then sine 5t made it wobble up and down in the z direction. So if I look down on this thing, I've got, looks like a circle. But then when I look on the side, of course, it's going up and down in the z direction. Maybe if I just make it be, 1 in the z direction, then it'll make a nice looking circle in space. But of course I've thickened it up so that so now there's a tube around that circle. This is kind of annoying because the axes are all different sizes. Let's do this. This will be a slightly wobbly circle in space. Yeah, that's pretty good. And it doesn't quite close up there, does it? Let's see. I guess that's because t goes from minus 3 to 3. Let's make t go from 0 to 2 pi. And it will close up. Yeah, that's pretty cool. It's like the one ring. So that's pretty neat, and you can put in other functions. Okay, yeah, I guess you don't necessarily want to see me just keep on. Here's another fun one. I change sine of t to sine of 3t. You can make a lot of really great curves in space. It's pretty fun. just to multiply these things by different amounts and see what kinds of crazy curves in space you make. And then this method lets you thicken those curves up, make some other complicated object. These are pretty complicated, right? And then when you look along certain axes, of course, they look like the regular Lissajous figures. Pretty fun. That's neat. It's pretty great. What other questions that people have? Ooh, ads. Do you see ads on this? Oh, I'm sorry. That's horrible. It's definitely really unfortunate, I gotta say. Oh, well, I'm sorry about that. I guess I'm not that surprised. I mean, this kind of uh, broadcasting, it can hardly be uh, free from their point of view. But hopefully, we'll eventually have a Zoom account at in available to us. We only have Carmen Connect right now. I had a lot of trouble using Carmen Connect, but wish I could up the number of samples in this thing. There must be a way to do that. Yeah, I mean, I really have a lot of. I've never actually. The part of the trouble is just my computer doesn't have a lot of things on it, so it runs into just untold problems usually with things like screen sharing. But this works for me, so that's good because I can just use FFmpeg to stream my screen to an RTMP endpoint. Yeah, it's hard to tell if this thing crosses itself. It looks to me that it doesn't cross itself. It's kind of fun. It looks so complicated. If I could increase the number of samples, then we could look at cosine 7t, cosine 5t, sine 3t. Other questions that people have. Points in bound or unbounded. Um, let's see. Do you mean like when you have a region and you might have this region is bounded, but this region out here is unbounded? Okay, so you want to have like a set. So I could write a set S consisting of all the points x and y in the plane with the property that x squared plus y squared is bigger than 100. And this set is unbounded because there's arbitrarily large xy, so there's points that are arbitrarily far from the origin for which this condition is satisfied. Oh, you mean in the section on continuity? You want to look at that? Let's move to, here's continuity. So yeah, here they're giving you definitions of when a set is bounded and unbounded, and let me maybe draw another picture here. So this is a definition that's true in general, in Rn. But if you just look in the plane, right? If you want to know, is this set, if you're thinking of the set of points that are in this region, is that set bounded? It's bounded because there is an open ball of radius m which contains this set. And a set that's not bounded is called unbounded. I love definitions like this. But that, an example of that is, say, if you've got a set, say, that looks like this. It's this strip that goes on forever. I mean, no matter how large of a ball you end up looking at around the origin, no ball is ever going to contain this infinite strip. So that infinite strip is unbounded. This language about open balls is really the same thing as whether or not there's points in there that are arbitrarily far from the origin. Right? If a set is contained inside, if a set S is contained inside an open ball, I mean that really just means that all the points of S are no more than big M away from the origin. Does that help a little bit to think about unbounded and bounded? Yeah, if a set is contained inside any open ball, so I mean, if you just pick some open ball, here's an open ball radius m, and you pick anything inside here, it could be quite evil looking. Um, that set is bounded because it's contained in the open ball of radius m. I would be worried about talking about graphs at this point. I mean, if okay, yeah, so the points, the set of points outside of this circle is unbounded, not because it's outside this open set, but because this open ball rather, but because it's outside every open ball. If you take a look at say the plane, and you subtract an open ball of radius 100 around the origin, right? That, take the plane, take the ball of radius 100, remove it from the plane. What you're left with is all this stuff out here. No matter how big of an open ball you draw, there's always more stuff out here. So this thing here, the complement of a ball of radius 100, all the points in the plane which are more than 100 away from the origin, or at least 100 away from the origin, this set is an unbounded set. So yeah, the set of points outside of some open ball is unbounded. When you're talking about the graph of something, I mean, you have to be a little bit careful because you have to sort of tell me how you want to build the graph. I mean, if you're talking about whether or not a graph of a function is unbounded, I mean, there's a couple different reasons why the graph of a function could be unbounded. It could be unbounded because the domain is very large, right? It could be because the domain's unbounded, or it could be because the image of that function is unbounded, and those are pretty. Oh, yeah, okay. So if it's like f of x y equals the square root of something, I mean, if the rule for the function is f of x y equals the square root of, I mean, just to be super concrete about it, like if you're thinking about f of x y equals, the square root of 10 minus x squared minus y squared, say, I mean, this rule is rigged so that the domain of this function is the ball of radius root 10. So the domain's not too big, and then the outputs of this function, Well, I mean, x squared minus y squared, as small as that can be, is you could make this be zero, which means you can't make this thing any bigger than root 10. And that means that the possible outputs of this function are also constrained. So yeah, the graph of this function then is bounded. See, what's confusing though is that whether or not the graph of a function is bounded or unbounded is not the same thing as whether or not the function is bounded or unbounded. We say a function is bounded if there's some big M so that the function's output is never bigger than m or smaller than negative m. But to say that the function's graph is bounded is to also assert something about its domain. And I definitely don't want to say. I mean, I don't want to conflate those two ideas. Yeah. So here, I mean, this is talking about whether or not a set is bounded. Yeah, I mean, in this case, this function is bounded and its domain is bounded, uh, and consequently, its graph is bounded. But that's really that I mean, you could certainly have a function which is bounded, but for which the graph of the function isn't bounded. I mean, a naive example of this is something like the function f of x equals 17, where I think of f as a function from r to r. The graph of this function just looks like this, but I mean this line, which is the graph, is not bounded. Yeah, so you could have an example where the domain is bounded. You could have a situation like this where the domain is between, say, -1 and 1, but the function's graph looks like this. You could build an example for this by appropriately scaling arctan if you want. So this would be a situation where you could rig it so that you could define a function whose domain is just between -1 and 1, but whose output can be any real number, and that's not a bounded function. And then in the previous example, where the function was given by the rule f of x equals 17, I mean the function is a bounded function because the output of the function is it's no bigger than 18 and no smaller than 16. So I mean it's bounded, but the graph of the function is unbounded. It goes on forever. So this is really talking about sets, and often here in the section on continuity, we're introducing a lot of this language, because it provides a slightly fancier way if you want to think about questions about continuity. It provides a language that'll be helpful for us when we start to think about constraints. And I mean these three ideas about open, closed, and bounded, and how they're related are just wonderfully deep. I mean, there's so many great things to say about whether or not, say, if you have, I mean, the questions we're thinking about here are questions where we have a bounded domain which is being sent to an unbounded set. So you can have a function whose domain is a bounded subset of the line, but whose image is an unbounded set. Uh, and that maybe that's surprising. I mean, from some point of view, I mean, the fact that functions don't preserve boundedness, that you can have a bounded thing that goes to an unbounded thing. But then, you can also ask whether or not functions preserve being open or being closed. And I mean, maybe it's not. Anyway, I mean, there's a lot to say about exactly how functions get related to concepts like open, closed, and bounded. Maybe I should stop saying things now. But other questions that people maybe have. Yeah, that's an interesting question. Will you ever have limits that are have this 0 over 0 form, but not because something cancels, but they do exist? Yeah, I mean, one sort of classic example, I mean, if you want, the limit as x goes to 0 of, say, x over sine x is an example of this. And, I mean, that's in two variables. Oh, okay, okay. Well, I mean, if you want more variables, I'll just add y on the top here and say y also goes to 0. Let me draw that in the usual way we'd write this. So the limit of xy goes to 0. The limit as xy goes to 0, 0 of, say, x plus y divided by sine of x. Um, I mean, I guess I can just write. I mean, I can just keep writing things here. Plus sine of y. Um, what what happens in this case? How would you uh, analyze something like this? We don't have I mean, you can't. You're not going to do any sort of cancellation of 0 over 0 in a case like this. And maybe you're hoping for some sort of L'Hopital thing, but I wouldn't recommend that certainly. Maybe it's easier just to think about a case like this. I mean, x plus y divided by sine of x, um, and what happens in a case like this. So this is sort of an upsetting case because this denominator doesn't make sense when x is equal to 0. But the domain of this thing uh, is away from this line. It certainly makes sense near that line. Um, things around. Moving things around practice problems. Where are the moving things around practice problems? Are they just on Chimera somewhere? Yeah, where though? Maybe in Bart's world? I don't know. Did he add them here? Never really know. Yeah, modules. See, I've got the calendar and syllabus, the textbook. Oh, these things here, I see. These are from the recitation. Yeah. Okay. Um, yeah. So this kind of problem here. Let me zoom in a little bit. Um, is is really asking you to think about the fact that computing scale of vector xy onto j really amounts to calculating y, and computing the scalar projection of the vector xy onto the standard vector I is the same as x, the number x. So this kind of equation is actually computing the same thing as y equals x squared. And that's true again here. I mean, it's uh, here I've changed w and I've changed I and j, and now I'm using W and V. W and V, I mean, they're not the same as I and J, but they're still orthogonal to each other. They're not unit length. But then the result of imposing a condition like this is going to amount to carving out a parabola in the plane. It's just the parabola now is it's going to have W is going to play the role of J, and V is going to play the role of I. So it's going to look like a parabola which has, but it's been tilted somehow because V and W are like a tilted and stretched version of I and J. I mean, they're still orthogonal, but they're longer. V and W are longer than I and J. So you'll end up getting something like a parabola, which is pretty neat. I mean, it's a neat trick to be able to transport knowledge that you have about, say, parabolas in the plane, but now you can build, tilted parabolas. And if somebody came up to you and said, "Oh, I really need some equations for some tilted parabolas," I mean, you might have a real trouble coming up with equations for tilted parabolas. But if you can somehow transport your knowledge about tilted parabolas into this case, that's pretty helpful actually. So hopefully that makes some sense. Okay, no problem. I'm really happy to be able to talk with people in this sort of bizarre internet place. Other questions that people have. Okay, I'm glad that you all of your problems are gone. No more problems. Okay, well, I should probably go to bed. Make sure that I'm awake for tomorrow morning. Hopefully, I'll see some of you tomorrow morning, or at least the folks of you that are in my section. Well, thank you. I really appreciate you all making it at this crazy time at night. So I will. I'll see some of you tomorrow, and we can talk some more about continuity and limits, and we can experience the awesome fury of the partial derivative, which should be really great. I mean, I think it'll provide a lot of insight. These functions of several variables, in a way that maybe the derivatives of vector valued functions didn't seem different enough. Okay, all right. So I'll see you all tomorrow. Have a fun night.